All right, guys at home, it's going to be a great Monday. I just ran through this whole thing and forgot to hit record, so I have to do it again for you people while they're working. A couple little updates. First of all, I told them that I'm going to try to shorten the notes a little bit, and also I'm going to shorten the chapter. I'm going to cut it into two different pieces. I think a lot of times when you're at home and watching 40 minutes of notes, that seems like a lot. Normally in class, we would do 10 minutes, then group up and do one, and then 10 minutes more, and there's breaks. But without breaks, that's a lot of notes. So I gave them a new note packet, and yours is linked right here where it says new note packet. You'll notice it's a lot thinner. And these guys were done by 10 to 8 today and have 40 minutes almost to work. I'm going to try to do that. I can't do it all the time. So it's not a promise, it's just what I'm going to try to do. Next up, I gave the tests back. If you think you're eligible to do a test fix, the directions are on this eligibility form, and then the submission for it is right below. So there's two Google forms. Do the eligibility one first if you think you did what you needed to do to fix that a little bit. And that applies to anybody. I leave the highest score at 97, but if you have a 94 and you want to fix up to 97, I allow that. I leave the top A's for the people who did it the first time, but I do put a cap on it. But it's not only for people who got an F. If you got a B plus and you're like, oh, I did silly mistakes and you're eligible, I would do it. It's not super labor intensive. It depends on how many you got wrong. So you'll find the details in here. I don't make you retake the whole test. I don't make you fix the whole test. I don't make you do a packet on the whole chapter. If you got an 88 and you're eligible, there's not a whole lot of work to it. If you got a 62 and you're eligible, there's more work to it. All right. Next up, the ACT is tomorrow. So you B group kids, because I was gone Thursday, it's going to be a week and a couple days since I've seen you, so really reach out to me if you need some help. But we're going to dig in and start these new notes right now. And it starts off with some review. So the notes will be about 15 minutes long, and then the assignment for today is the delta math. Not quite sure how long that'll take. How long is it taking, guys? Is it going pretty fast? Yes. All right, so up here, we're just going to do a little bit of review of two things from last week. One was the formal definition of the derivative. And I'll tell you, you will never have to do it again. You'll just have to recognize, well, I shouldn't say that because there's a Flipgrid assignment tomorrow where I do have you do one of them the long way, but after that, you'll never do it again. The whole rest of the chapter is about how do we make that derivative process a little quicker. So remember, the formal definition, or sometimes it's called the limit definition, is the limit as h approaches 0 of, and I explained all this in detail and derived it in last week's notes. But this is the change in y over the change in x. This right here is the slope of a secant line. And as we have that change in x, what we call the h, the change in the x's approach 0. So we get closer and closer and closer. The slope of that secant line starts to approach the slope of the tangent line. Your goal is not to do it anymore. You just need to figure out what's the function and at what spot are they doing it. The best thing to do is find the x plus h and highlight it. So 9 plus h, which means x has to be, or they're calling it c. The c in this problem is 9. Okay, I can see it. What function is the x plus h being plugged into? The square root function. So f of x is equal to the square root of x. And then I asked them, I said, well, where is this minus 3 coming from? And that's from here. It's f of x plus h minus the square root of x. And the square root of 9 is 3. So the best thing to do is just locate that x plus h. In the notes, I said sometimes h is also called delta x. So make sure you understand that this is the same notation. Here's my x plus h, x plus h, x plus h. So you can see, even over here, you can see what the f of x is, because we always subtract f of x. But it was x cubed minus 5 x squared plus 4 x minus 7, right? That's the original function. So here's f of x plus h minus f of x. So all I needed to do is spot it, and this would be at c being any x value. Now, had there been a 1 here and a 1 here, it would have been at c equals 1. Now, from last week, I gave you the power rule briefly so that you could find the derivatives quicker for doing the slope of the tangent line. And remember, the power rule for finding the derivative says you don't need to like cube all of this and FOIL this and distribute the 5 and distribute the 4 and combine everything and factor out the delta x and cancel it and replug. When you do, you get the derivative, and the derivative can be found by bringing the power out front and knocking it down, minus power out front and knocking the power down. The linear terms always go to the constant in front of it, which is 4, and the constant terms always go to 0. So had you done this the long way, you would have gotten that. All right? The next review we did is we have some line, 2x plus 3y equals k. It's tangent, which means it nicks it once on the outside of the curve, and it's nicking it where x is equal to 5. So I don't know what that function is, but I'm going to make a fake one. I'm going to have my tangent line, 2x plus 3y equals k. I'll do it in red. Nick the function right here. It says, what is the value of? Well, you have to understand that this is that alternative form of the derivative. As x is approaching c, if you didn't watch the notes last week, you have no clue what this is. It's the alternative form for the derivative at that specific spot. Not as a function of x, but a specific number for the slope of the tangent line right here. So they're asking me for the slope of the tangent line. They gave me the tangent line. So when I asked these guys in first hour, I said, well, how do you get the slope of this line? Somebody said, put it in slope-intercept form. I said, yes, just do it in your head. So you'd subtract 2x and divide by 3, which gives you a slope of negative 2/3, which would be what the derivative is there. So notice there wasn't a lot of work to do. And I told you I'm going to be far more AP focused because I'm trying to slim stuff down here. And this is AP calculus. So normally I try to intermix calculus like it is in college with AP. You might say, which one's easier? It depends. AP is harder if you don't understand the concepts. College is harder if you're not good with a bunch of really difficult manipulation. So the derivative of a graph with sharp turns. So up here, I want you to write 3 conditions in which a derivative does not exist at c, technically, at x equals c. So when we have what's called a sharp turn, or some books call them cusps, we're going to also make sure we know how to write it with the calculus notation in case that's required. But when a graph is smooth like this, and I ask for the derivative right here, or the slope of the tangent line, you'll notice that the slopes from the left are approaching the slopes from the right. They're collapsing in on the slope at that point. But when I have a sharp turn like this, the slopes from the left are vastly different than the slopes from the right. Loosely stating it, your curve has to be like roly-poly. It can't have sharp turns like the absolute value of x minus 2 does. This has got an issue right here because the slope to the left is -1, or the derivative to the left is -1. The derivative from the right is +1, and those two aren't approaching each other. Now, if I had it smoothed out there, let's go like this, then from both sides, the slope's approaching 0. So we would say not differentiable, or f is not differentiable. I'm just going to write diffable at x equals 2 because with words, there's a sharp turn or there's a cusp. But with the limit notation. If you're asked to use, there's on the AP exam like 2 years ago, they were asked to use limit notation to explain it. If they don't say use limit notation, you can say there's a sharp corner. If it's just a graph like they're doing on Delta Math, they're spotting sharp corners, right guys? Was that easy? Are you done with that part already? Yes? So they're spotting the sharp corners, but if you have to explain it with limit definition, you have to say the limit as I come in from the left of the derivative, which is -1, does not equal the limit as x approaches 2 from the right of the derivative. I told them I've been a reader for this in the past, and a lot of kids forget the derivative on here. They think of it as being the original function, but the original function actually, the limit as I come in from the left of f of x, or the y values, is equal. They're both 0. So be careful with that. So first situation, sharp corners. Second situation is the vertical tangent lines. Right here at C, when I'm coming in from the left and I'm thinking these slopes of these tangent lines, they're approaching infinity. When I come in from the right, they're getting more and more and more and more and more negative. So they're not approaching each other, and my tangent line is vertical. And in algebra 2 or 1 or whatever, we learn to write the slope is undefined for vertical lines. We'll write d and e. But remember, the slope is the derivative there. So we'd say the derivative does not exist where there's a vertical tangent line. Don't worry about this. It's exactly what I said. When you're going to infinity from the left and then from the right, positive infinity, or vice versa, the most common graph that has a vertical tangent line is the graph of f of x equaling the cubed root of x. And I had the guys give me numbers that were nice to take the cubed root of. The first thing that popped out was 0, and I said yes. Then somebody said -8, or no, +8, and I said, yeah, that'll work out here. Then somebody said 27, Ellie, and I said, I don't want to go out to 27. And then Frankie chose 1, and I was like, oh, thank you, Frankie. And then he also chose -1. I said, thanks again. He's on a roll today. Right, Frankie? Yep. And I said, when you do the graph of this, you get a vertical tangent line right in here at 0. Now I'm going to have you see the analytics or the algebra back that up. So let's suppose I wrote the function so that I could see its power. The power rule says, and we're going to do more with the power rule tomorrow. I just gave you the very basics of the power rule to make your life easier last week. So you weren't going through that whole limit process when you really could just bring the power out front. And then we knock it down 1, disguised as denominator over denominator. And then I asked, what do you do with the negative exponents? And young Jakey said, put it in the denominator. I said, true that. And then I said, well, what number can't we divide by? And I think Felicia said 0, but I'm not sure. No, it was Mallory. So x can't be 0, and you can see that it's backing up on my graph. That vertical tangent at 0 is causing an algebra issue with the derivative as well. So if I didn't have the graph where I could see it, or if I couldn't make a graph, you look for where that denominator equals 0 for a vertical tangent line. So kind of keep that in the back of your head, because we can't divide by 0. So we have these two situations. And I had them in class. I said, go draw this one. And take care of this first situation where you're going to have a sharp turn or a cusp at C. Didn't matter where they put their C, as long as they came in nice and whatever and then took a sharp turn there. Doesn't really matter. That is not differentiable at x equals C. For the other situation, doesn't matter where you put your C, but as you come in from the left, and that you should kind of make that vertical tangent line change there, where it seemed like you were heading to infinity and then abruptly changed. Okay, so for both of these, the derivative doesn't exist. I'd also challenge you, though, that there's a third situation. If I asked you, what's the derivative at x equals 3? You'd say, well, there's no dot there. How can I draw a tangent line? So the other thing that's required is continuity. So last up, differentiability implies that the function must have been continuous. I always tell kids, think Diet Coke. that if it's differentiable, it had to have been continuous. The converse of that, which is when we switch the if and the then, which would be if the function's continuous, then it's differentiable, is not true. The most logical contrapositive to that is that absolute value graph. I just did not lift my pencil. I made a very y equals f of x function that was continuous, but I took a sharp turn at c. So you look for three things when you're looking off of a graph for places where a derivative doesn't exist. You look for sharp turns, you look for vertical tangent lines, and you look for any kind of discontinuity, be they a gap, a hole, or an asymptote. No derivative at c, no derivative at c, no derivative at c, no derivative at c, and no derivative at c. Okay, so that's what you're looking for on a graph. Last step. Estimating the values of a derivative numerically. This is always on the AP exam. You always get a problem that has a table. And then there's usually 3 or 4 questions that deal with derivatives, limits, and integrals. This first one deals with the derivative. That's what T prime means. First, make sure you understand what this is charting. This is the temperature in Fahrenheit of a polar bear as it's getting colder and colder over minutes. So this is T in minutes. The minute it says T prime, you're thinking derivative, you're thinking slope. The reason it says estimate is I don't have anything here at 5.5 minutes. So I don't know what's happening there. So what we do is we stay as close as possible. I call it straddling it. And graphically what it means is if I wanted to find the slope of the tangent line right here, my best estimate, if I didn't have it, would be to use the 2 points closest that I'm given and find that slope. I wouldn't use like these over here, right? So you get as close as possible. So you find that spot on your table, and then you say, well, the derivative, the rate of change in temperature, that's what a derivative is. It's a rate of change or slope. We do change in y over change in x. So we do y2, t of 6, minus y1, t of 5, over x2, 6 minus 5. I told you these were eventually going to functions changing over time. Then you just go grab them off your table. 90.45, just algebra 1, minus 90.73, all over 1 minute. And you can just leave that. It's going to be negative. We're going to learn that when derivatives are negative, it means functions are decreasing. That makes sense, right? Slopes are negative, the function must be going down. But let's label it. This is in temperature on the top, which is measured in degrees Fahrenheit, per time unit of minutes. All right, so that's it for today. The assignment is a delta math. Have a good one. I'm still recording.